So in this lecture, we will look at how to estimate the daily dose, and for example potential, and also the applied daily dose. So potential daily dose is often written as the average daily dose or ADD, and this is our basic exposure to effect pathway. So the chemical is sort of, we are exposed to the chemical, and the amount that is entering the nose and mouth is our potential dose. Then we have intake into the lungs, where we have the applied dose. Then so some absorption, not everything is absorbed, not everything of the potential dose is absorbed, and whatever percent is absorbed is our applied dose. And this becomes, when it is uptaken and reaching the bloodstream, that is our internal dose. And then it, uptake and metabolism, and this is reaches the organs, and we have the biologically effective dose, which then cause the effect. So we can estimate the potential daily dose or average daily dose, this part, if we know the concentration of the chemical in the air. So ADD or average daily dose is the product of contaminant concentration, the inhalation rate, exposure time, exposure frequency, exposure duration divided by the average time and the body weight. So this is the amount uptaken per kilo body weight per day or per hour, depending on what is the unit of the averaging time, generally being days. So ADD is then equal to C air, which is the concentration in air, and this could be milligrams per meter cube. So I will just write the concentration here, milligrams per meter cube. Inhalation rate in meter cube per hour. So how much air we are inhaling per hour. So this is milligram of contaminant. So I'll just write milligram of X per meter cube of air. And we inhale meter cube of air per hour. How many hours per day is our exposure time? So how many hours per day are we exposed to this contaminant? How many days per year we are exposed to this contaminant? So let's say 5 hours per day, 20 days per year, for example. What is the exposure duration? How many years this events happens? Divided by the averaging time and the body weight. So averaging time is days and the body weight is kilogram. So averaging time days, meaning we are trying to find the exposure duration in a day. So let us see what ADD will come out. So meter cube per year will cancel, H and H will cancel, D and D will cancel, Y and Y will cancel. So we will have ADD as milligrams per kg, and this is our body weight, kilogram of body weight. So generally it is often written as kg BW. So people know what we are talking about. We are talking about kilogram body weight. So I will just write the same way, kilogram body weight per day. So we have arrived with the simplest. Now the best way to get this concept of probable or potential daily dose or the average daily dose is to do an example. So let us say we have a chemical, that chemical X, which is a flame retardant. So it is used in many consumer products such as furniture textiles. So the upholstery on the sofa, or maybe it's a carpet in a room, construction boards, automobile interior textiles, etc. The goal of this chemical, let us say, is to delay and inhibit fire, delay or inhibit the spread of fire or the initiation of the fire event. So human exposure to X can be through inhalation of dust, through ingestion, or through dermal exposure. So in this particular example, we will focus on the inhalation only. So assume that during a 10-year service time of textile, let us say we have a carpet, and the carpet is in a office space. So a person will go in the morning for work where this carpet is and then come back in the evening. And that the service time of this textile is 10 years. So assume that during a 10-year service time of textile, a total of 100 milligram of X is released per meter square of textile. So the first thing is we will read the question through and then start one by one, because there are other elements that need to be there in part 1. The first is illustrate the problem by means of a figure or a conceptual sketch, let us say. Then we have numerical, which is what is the release rate in mass per day of X if the total area of textile is 6 meters square. Further, if the volume of this big room is 80 meter cube and the air ventilation, so this is basically our fraction of room air that is replaced with clean air per day, is only 0.35 per day in this hypothetical room. What is the concentration of X in this airborne dust, or what is the concentration of this X at steady state? How long does it take for this concentration to reach 90%, 95% of the steady state value? So let us say we start at time t equal to 0 and we have a steady state concentration. How long will it take for the concentration to reach that steady state value? To reach 95% of the steady state value. Then we have, if the body weight of the human that we want to get the exposure of is 70 kilogram, what is the adult's potential daily dose and applied dose in milligram per kilogram body weight per day averaged over the 10-year cycle if the human in this room is for only 8 hours every day for 5 days a week? So this is sort of a working environment, 8 hours per day, 5 days a week. Then we have been told assume 90% absorption efficiency, and we have also been told that the individual in question inhales 15 meter cube of air per day. And for this part, getting the daily dose, we have to assume the concentration to be 95% of the steady state concentration. Okay. So we have a textile with a service life of 10 years. Over this 10 years, it emits 100 milligram of X in 1 meter square. The total area of textile is 6 meter square. The volume of room is 80 meter cube and it is basically exchanged at a rate 0.35 per day. So we have to first calculate the steady state concentration, and then we have to tell how long will it take for the concentration to reach 95% of the steady state value. Then if there is a human in this room, what is the human's daily potential daily dose and the applied dose over this averaged over the 10-year cycle? We have been told that the person only goes to this place 8 hours per day for 5 days a week. The absorption of X is 90% and the individual inhales 50 meter cube per year. We have to assume that the concentration being inhaled by the human is 95% of steady state concentration. So this is actually our whole big question, and often we would be post with only the last part in our in real life. Maybe we will be told that 100 milligram is released per meter square in 10 years, or we will do some emission test about release. But then we will be told that okay, this is the air exchange rate, and we want to calculate the dose of the person over this 10-year cycle or whatever number of year of cycle. So this is a very sort of big question if we read and we think of the scope. So given all the information that we have read in the question, let us try to solve this one by one. So first we will look at illustrate the problem by means of a figure. So we can just draw the figure in this sheet itself. So let us say we will be in a room. The concentration inside the room is C and the volume is V. Further we know 100 milligram is emitted. So first we will just go by emissions. We will do the calculation in a bit. So we have some emissions, and we also know that there is a air change or air exchange rate. So we have the fresh air coming from outside, which we will assume is completely clean air. So we will have some air coming in and some air going out, and this would be at some K exchange, so rate constant for exchange times volume. So this much fraction of clean air comes in and this much fraction of clean air goes out in terms of volume. If we have a mass inside the room, then here anyways clean air is coming, and the amount that will go out of the room will be KeV times C. How? So Ke times V is the volume going out. Let us calculate per day, meter cube per day, because Ke is 1 by day and volume is meter cube. So this much volume is going out per day, and C is the concentration here, and let us say this is a microgram per meter cube. So this all becomes uh, the total outflow will become microgram per day, and only clean air is coming, so we will have concentration 0 multiplied by K times V, so this will be 0. So we will draw the figure again. So we have the room with concentration C, volume V. Let us just write inflow right now, or input, inflow and outflow, then emissions. This is only what we know, because we know there is a air exchange with the outside and there is a emissions. So I is our inflow. Let's say I will let's say micrograms per day. O is again in micrograms per day. O is outflow, again in the micrograms per day. E is emissions. I'll just and again micrograms per day. C is equal to concentration of X in the room in micrograms per meter cube. Okay, and the emissions is the emissions from the carpet. So I can just if you want, from the textile. From emissions from the textile. So this is sort of the conceptual diagram, and we will carry over this diagram in the next going forward. So the next is, what is the release rate mass per day of X if the total area of the textile is 6 meters square. Okay, so we have in 10 years the textile emits 100 in, so let's do the solution here. In 10 years the textile emits 100 milligram per meter square. The total area of textile is 6 meters square. So we will have in 10 years the textile emits how many? 100 times 6 milligram per 6 meters square, right? Because our overall textile is 6 meters square. Oh, sorry, here 6 meters square. So in 10 years time, if 1 meter square emits 6 milligrams, then 6 meter square will emit 6 times 100 milligrams. Now what we want is the total rate mass per day. So then this becomes, I will continue within this. So this will become 600 milligrams over 10 years. So the textile is going to emit 600, total of 600 milligrams over 10 years. So what about per day? Per day the textile will emit 600 divided by 10 years multiplied by 365 days per year. Right? So 600 is here, 600 milligram over 10 years. So over 10 years is 10 times 365 days. So this would be 600 divided by 10 divided by 365. So it is 0.1644 approximately milligrams per day. So this will be, we will convert it into micrograms. So this will be 164.4 micrograms per day. So we have our answer here, 164.4 micrograms per day, and this is equal to our E value. Okay, so our figure, we had a emission, and this is 164.4 micrograms per day. So what is the next question? Further, if the volume of the room is 80 meter cube and we have the air ventilation, the air that is replaced with clean air, what is the concentration of X in the airborne dust at steady state? So let us define our room again for refreshing. So I inflow, outflow, emissions, concentration C, volume V. Now let us assume the mass is m. So m is equal to C multiplied by V. So let us assume mass of X in the room as m. So m will become m at S equal to CV, and inflow, outflow and m. So again, what is our mass balance equation? So the mass balance equation will be dm by dt equal to, what are the total inputs or total sources, I plus E, and the only output or sink, the only outflow, the only sink is the outflow. So I plus E minus O. Okay, so now we will go one by one. I am just going to write the equation at the top. Dm by dt equal to I plus E minus O. So okay. Now volumetric flow is volumetric exchange. So we have volume of air. Volume of air that is coming in or out is basically the fraction of air, that is the fraction of volume. The fraction of room air that is replaced with clean air is 0.35 per day. So 0.35 of this air is coming in and out per day. So this would be 0.35, which is 1 by day, multiplied by the volume. So let us say we will define this as K exchange. So the or K replacement. So let's define as KV. V is the ventilation. So we'll define this KV. KV equal to 0.35 per day. So I would be C ambient multiplied by KV multiplied by volume. Now we are told that the air is clean, so we will assume C ambient is basically close to 0. So I will just become 0. E we have already calculated. E is 164.4 micrograms per day. So we have E equal to 164.4 micrograms per day. O is the outflow. So this is equal to the concentration in the room multiplied by kV multiplied by volume. So we will keep this. Also we know M is equal to V times C or C times V. So how will our mass balance equation now look like? So volume does not change with time. So dm by dt will become V dc by dt equal to I, which is 0, plus E minus output. So I will just say this is 0 so that you are not confused with the O. This is outflow. So I will just make a proper 0. So 0 plus E minus C K V times V. So we will get rid of this and have our dc by dt equation. V dc by dt equal to E minus kV multiplied by V multiplied by C. So the general first thing was, what is the concentration of the airborne dust at steady state, and how long does it take for the concentration to reach 95% of steady state value. So we will first look at first part. What is the concentration in the airborne dust at steady state? So at steady state, there will be no change in concentration. So at steady state, dc by dt becomes 0. So we will say C is equal to C steady state, and then that will mean E is equal to kV times volume times C steady state, which implies C steady state is equal to E divided by kV times V. So if we put in the values, we have CSS equal to 164.4, and I'm going to write the units in the bracket, micrograms per day divided by 0.35 the unit is per day, multiplied by volume. Volume was 80 meter cube. So we will have 80 meter cube. So this is going to be our steady state concentration. So if we just calculate this, this is going to become 164.4 divided by 0.35 divided by 80. So this will become 5.87 micrograms per meter cube. So this is our first part, steady state concentration. The next part was how long will it take for the concentration to become 95% of the steady state value. So we have the question framed is at what time C equal to 0.95 of CSS. So the general solution or the solution to the solution to that differential equation is the equation dc by dt v dc by dt equal to E minus kV by V by C. So we will write that, we will rewrite the equation. Differential equation is we will just write the V on the other side. So dc by dt equal to E by V minus K V C. And the solution to the differential equation would be C at time t equal to E by kV times capital V 1 minus e to the power minus kVt. And we already know this is CSS. So this is equal to CSS 1 minus e to the power minus kVt. Now we want to get T. We want to know T at which Ct is equal to 0.95 CSS. So let us just put this value now. I'm going to change the color. Let's do this one. So maybe it's better. So we have 0.95 CSS equal to CSS 1 minus e to the power minus kVt. So we will cancel the CSS now. So we will be left with 0.95 equal to 1 minus e to the power minus kVt. Now we will rearrange this equation on the next whiteboard. So we get e to the power minus kVt is equal to 1 minus 0.95. So this is equal to 0.05. So minus kVt will be equal to ln of 0.05, which is equal to ln of 0.05 is approximately equal to minus 2.996 minus 2.996 0.96, so we will just approximate it as -3. So T is equal to -3 by minus kV. So this will be equal to 3 by 0.35, and kV is actually per day. So this will be 3 by 0.35. Around 8.6 days. So we see that within, although the service time of the carpet or the service time of the textile is 10 years, the concentration due to the emissions from this textile are already reaching 95% of the steady state concentration in 8.6 days. Okay, and the 95% concentration is, we need this C, so we will write C95 0.95 CSS, and this is equal to 0.95 into, our CSS was 5.87 microgram per meter cube. So 5.8, I'll just write 5 properly, better, 5.87 micrograms per meter cube. So C95 will be 0.95 times 5.87. 5.87 multiplied by 0.95. So this is around 5.6 microgram per. So this is our concentration, which is 95% of the steady state value, 5.6 micrograms per meter cube. Now let's see the next part. And for reference, I am going to quickly write this. C95 is equal to 5.6 micrograms per meter cube. Okay, now if the body weight of the human is 70 kilo, what is the adult's potential daily dose over this 10-year cycle? If the human is in this room only for 8 hours every day, for 5 days a week, and then assume 90% absorption efficiency, individual inhalation, and the concentration. Okay, so we have to write what parameter is what. So this is our, so we know what is our potential daily dose, basically is equal to ADD. How long we have to average? Averaged over 10 years. Averaged over 10 years. Okay. Now what is our equation of ADD? ADD is equal to C, I'll just write C95 multiplied by what is our equation for exposure time. So let's just go up. Let's just go back to our ADD equation. Inhalation rate multiplied by exposure time, exposure frequency, exposure duration divided by averaging time in days divided by the body weight. So we will have this C95 C95 multiplied by inhalation rate multiplied by exposure time times by exposure frequency, exposure duration divided by averaging time multiplied by body weight. So now what is what? So C95 is 5.6 microgram per meter cube. Inhalation rate is we'll do black color now. Inhalation rate is equal to 15 meter cube per day. So we need to change it to per hour. So 15 meter cube per day becomes 15 by 24 meter cube per hour. So this is equal to 15 divided by 24. So 0.625 meter cube per hour. We have inhalation rate done. Exposure time is 8 hours per day. Exposure frequency is how many days per year? 5 days a week. So exposure frequency becomes 5 by 7. So in 7 days, 5 days are occupied. So 5 by 7 multiplied by 365. So these many days per year. Because every 7 days only 5 days are occupied. So the fraction is 5 by 7 and multiplied with the total amount of days in a year. So 5 by 7 into 365. Exposure duration is 10 years. Then the next thing is averaging time. So averaging time, we have to get the average over 10 years. So averaging time is 10 multiplied 365 days. And of course we know what is our body weight. Body weight is 70 kg. So now let us calculate our average daily dose first. So ADD will be equal to concentration. So concentration is 5.6 multiplied by exposure inhalation rate 0.625 meter cube per hour. So 0.625 meter cube per hour. So I'll just going to write the units here. Meter cube 0.625 meter cube per hour. Then exposure time is 8 hours per day. So 8 hours per day, our exposure frequency is these many days per year. So we have 5 by 7 into 365 days by year multiplied by the exposure duration 10 years divided by averaging time. So average time in days, so 10 into 365 and multiplied by the body weight, so 70. And I will just fill a bracket here. So let's just use, and the units would be 1 by day multiplied by kg body weight. So first, so then when we compute all this, we will do now average daily dose will be how many micrograms per kg body. So let us just first calculate the units. So I mean meter cube cancel, hour cancel, day cancel, year cancel. So our dose is going to be in micrograms per kg body weight per day. And what is going to be the value? Let us just quickly calculate this value also. 5.6 into 0.625 multiplied by 8 multiplied by 5 divided by 7 multiplied by 365 times 10 divided by 365 by 10 divided by 70. So we can even simplify this here. 365 and 365 will cancel. I'll use another color. So this one. So 365 and 365 cancel, and 10 and 10 also cancel out. So we will have a much simplified equation, which would be 5.6 multiplied by 0.625 multiplied by 8 multiplied by 5 divided by 7 times 70. So this is equal to 5.6 0.625 multiplied by 8 multiplied by 5, 140 divided by 490. So ADD will be 0.286 microgram per kilo body weight per day. So average daily dose is done. The other part was applied dose. So we have been given 90% is the absorption efficiency. So we will use this information to have our applied dose. Applied dose is equal to 0.9 multiplied by average daily dose. So this is equal to 0.9 multiplied by 0.286. This will be equal to 0.9 multiplied by 0.286, 0.286. 257 approximately, and I'm going to write the units here: microgram per kg body weight per day. So in this way we have seen how, if we are given the concentration, actually if we are giving the release rates from emissions up to the exposure, how do we do the calculation? So this is a simple example that we knew the emission rate, we knew the characteristics of the air exchange. From that we calculated the expected concentration in the room. From that concentration we have gone through and obtained our daily dose, potential daily dose, and the average daily dose itself. So as an example, we have gone so far over the concept of risk assessment and exposure, and we have done the example of calculation of the average daily dose.